Welcome back to the Deep Dive. Think back just a couple of years ago,
Okay.
before that big moment, if you wanted a machine to translate text,
Yeah.
you needed one specific model. If you wanted it to write code, well, that was another model entirely.
Right. Totally separate things.
And then large language models just exploded onto the scene, and suddenly, boom, one single generalized system could pretty much do all of it.
It was this huge unification for natural language processing.
Exactly.
That shift. And that was the GPT-3 moment for NLP, wasn't it?
That's the one.
And, well, based on this stack of research we've been digging into, it looks like machine vision.
Yeah.
You know, the whole field of getting computers to see, it's going through that exact same, like, tectonic shift.
Right
Now.
Right now. Because currently, computer vision still feels very fragmented, right?
Totally. Highly specialized. If you, the listener, need object detection.
You grab a specialized tool, like YOLO or something.
Exactly. Need segmentation. That's a different tool, again, like segment. Anything.
It's all these bespoke, task-specific models.
But our mission today is to really dive into the evidence that suggests these new video foundation models. They're about to completely change that game.
Okay.
We're looking hard at one called VO3. The researchers are basically arguing it's becoming the first true general-purpose model for vision.
And the analysis is, well, it's pretty massive.
It's exhaustive, yeah. They looked at, what, over 18,000 generated videos?
18,000, wow.
Across 62 different tasks, just to show that this one model can now do the work that used to take, like, dozens of specialized ones.
And the key mechanism, the unlock, is this shift away from the old way.
Right. Specialized fine-tuning for every little task.
Towards zero-shot learning, just using simple prompts.
Basically, yeah.
Yeah.
Text in, and then this complex visual task just happens.
Without any extra training for that specific job.
Exactly. It's like the power of generative AI, but applied to visual stuff, unifying the whole domain.
Okay, let's really unpack that parallel with LLMs, because I think that's super helpful.
It really is the core idea.
LLMs got so good, so general, because they were trained on just unbelievable amounts of text from the internet.
Web-scale data.
With a really simple goal, right? Just predict the next word.
That's the generative objective. And that simple task forced them to build this kind of generalized world model, but based on language.
Okay, so how do the video models copy that playbook?
Well, they execute the exact same strategy, basically. VO3 is trained on web-scale visual data, images, videos, everything.
Also with a simple generative goal.
Yeah, very similar, like text continuation, but maybe more importantly, video continuation, predicting the next frame or the next few frames.
Okay, so that forces it to learn movement, cause and effect.
Exactly. The physics of the world, how things move, how the 3D world actually works. Because you can't predict the next frame accurately without understanding that stuff.
And that leads to this concept that, well, it feels genuinely new compared to LLMs, this chain of frames.
Yes. COAF, chain of frames. It's a great analogy. If an LLM uses chain of thought, reasoning step by step with words.
Like for a math problem or logic puzzle?
Right. VO3 solves visual problems by generating the solution frame by frame. As a video.
So it's reasoning across time and space, visually.
That temporal dimension, that continuity over time, that's absolutely key.
It's not just looking at a static picture, like a maze.
Right, and guessing the path. No, it's simulating the act of going through the maze, frame by frame.
So it's like playing the movie of the solution, not just seeing the final picture?
Precisely.
Oh.
And that fundamentally changes the kind of problems machine vision can tackle.
Yeah, that feels like a big leap.
It is. And we have to stress how fast this is happening.
Okay.
The sources make a big deal comparing VO3 to VO2.
Its predecessor.
Yeah, which came out only about 6 months earlier.
6 months? Wow.
And the quantitative jump, the improvement in capabilities in just that half year, it's huge.
Yeah.
It really echoes that kind of exponential scaling we saw with early LLMs.
So the architecture itself is scaling really well.
It seems like it. Suggests we're on a very steep part of the improvement curve right now.
Okay, so the researchers broke down all these capabilities into like 4 levels.
Yeah, kind of hierarchy. It goes perception, then modeling, manipulation, and finally reasoning.
Let's start at the bottom. Perception. Just seeing the world.
Basically, yeah. This is where all the classic computer vision tasks live. But the twist is, VO3 can do them zero shot now.
Just from a prompt.
Just from a prompt. Things like denoising a blurry image, segmenting objects out of a scene, generating edge maps.
Okay, standard stuff, but without special training.
Right, like for low-light enhancement. They
Yeah.
prompted it to brighten a dark picture, and it worked. Like 92% of the time. Just worked.
That's pretty reliable. You mentioned edge detection, though. There was something interesting there.
Oh, yeah, this was fascinating. So they gave it a complex scene, maybe like a forest floor with lots of detail,
Okay.
and they asked it to generate the edge map. And sometimes the map it generated had more detail
More detail. Then what?
than the human annotated ground truth. Like, it picked up the specific tread patterns on a tire hidden in the leaves or individual leaf shapes that the human labeler had missed or simplified.
Whoa. Okay, that is staggering. So the model isn't just matching the human data.
It's just the model might actually be limited more by the quality of our benchmark data sets than its own internal understanding.
It's potentially seeing better than the data we use to train or test it.
In some ways, yeah. It's a pretty profound point about how we even evaluate these things.
That's a huge aha moment. And does that sort of general understanding help with, like, tricky images, ambiguous stuff?
It seems to. The sources mention it shows these emergent abilities, like, that classic optical illusion with the Dalmatian hidden in all the spots?
Yeah, it takes a second to see it.
VO3 could identify the Dalmatian, zero shot. And it could even interpret shapes in Rorschach ink blots, apparently.
Okay, so it's moving beyond just pixels towards understanding meaning. Semantics.
Exactly, which leads nicely into the next layer up, modeling.
Modeling. So understanding how the world works, like physics.
Intuitive physics, yeah.
Oh.
World rules.
Yeah.
Because it's trained to predict what happens next in a video.
Mm-hmm.
It has to implicitly learn things like, rigid bodies versus soft bodies, how gravity works, air resistance, even basic stuff like flammability.
Did they test that directly, the
Oh,
physics understanding?
Oh, yeah. That's where some of the coolest examples are. Take buoyancy.
Okay.
They prompted, generate a video of a rock falling into water. And, well, the rock sank. It got that right like 83% of the time.
Makes sense. What about floating?
They tried. Generate a video of a bottle cap floating on water. And it floated correctly in 58% of the generation.
So it gets the basic density idea without physics equation.
Exactly. Just from observation built into the generation.
Yeah.
And it gets even more complex with optics.
Optics, like light and reflections.
Yeah. It could successfully model the way reflections appear on a shiny, mirrored sphere.
That's tricky.
And even harder, refraction. They tested viewing a scene through a clear glass sphere.
So everything should look upside down and distorted.
And it modeled that inversion effect correctly. That requires some serious internal simulation of how light bends.
Wow. Okay, and what about, like, interacting with objects? Did they test that?
They did. Simple stuff, but indicative, like a simulated visual Jenga. Could it show blocks being removed in a way that's physically plausible?
Did it work?
About half the time, yeah, 50% success rate. And object mixing, like prompting it to show fitting a book and an apple into a backpack.
Things that obviously fit.
Right. It got that correct about 75% of the time. So it shows this basic dynamic understanding of 3D space and object interaction.
Okay, so perception is seeing, modeling is understanding the rules. What's the third layer?
Manipulation. This is where the model doesn't just understand the world, it can actually, change it, edit it.
Okay, so this is where zero-shot editing comes in, things that usually need Photoshop or specialized software.
Exactly. Prompting it to, say, remove the background from an image. Or do complex style transfer, make this photo look like a Van Gogh painting.
In painting, out painting, filling in missing parts.
Yep, all of that. They even tested it on slightly more, intellectual tasks visually, like asking it to complete a Sudoku grid it was shown.
A Sudoku? How did it do?
Surprisingly, zero shot, got it right, 67% of the time for simple ones.
Just by generating the completed grid image.
Okay. And a really great example of this manipulation power is what they called scene composition.
Right, you mentioned blending things.
Yeah, taking an image of, say, a zebra and putting it realistically onto a photo of the moon.
Okay, just pasting it in?
No, that's the key. It didn't just paste.
Yeah.
It adjusted the lighting on the zebra, the shadows, everything, to match the really specific harsh lighting you'd get on the moon.
And it looked convincing.
They rated it as realistic about 75% of the time. That's pretty sophisticated understanding of light and form.
That's incredible. And what about controlling the manipulation more directly?
Yes. Visual instructions, using doodles.
Doodles, like drawing on an image?
Exactly. The example that really stood out was they took a photo of a parrot in a jungle.
Okay.
And someone just crudely drew like a winter hat and a scarf shape onto the parrot.
And prompted it to add them?
Yep, and Veo 3 generated the final image, photorealistic parrot, jungle background, but now it's wearing the hat and scarf, perfectly placed, perfectly lit.
Wow. How often did that work?
On that specific task.
Yeah.
100% success. It just nailed it every time. Shows amazing coherence between the visual doodle instruction and the text prompt.
Okay, that ability to manipulate really sets the stage for the final level then. Reasoning.
Right, and this is where that chain of frames idea really comes into play. COAF.
Where it has to solve a problem visually, step by step,
Yeah,
over time.
exactly. And the big quantitative results here are pretty stunning, especially maze solving.
Ah, the maze example again. So how did it do quantitatively?
The prompt was simple. Generate a video showing a red circle moving smoothly from the start to a green goal without crossing any black walls.
Okay. Standard maze task.
On simple 5x5 mazes. Veo 3. When they gave it 10 chances, 10 attempts to generate a correct solution.
Yeah. Pass at 10, they call it.
Right. It achieved a 78% success rate.
78%. That sounds really good for zero shot.
It is really good. But here's the kicker. Veo 2, its predecessor, just 6 months before,
How did it do?
14%. 14%.
14 to 78 in 6 months.
Yeah. That's not just steady improvement. That's like a phase change. It shows that this generative frame-by-frame COAF approach is unlocking visual reasoning incredibly fast.
That is a massive leap. What else falls under reasoning?
Well, things like visual symmetry, completing patterns. It also got much better than Veo 2 and other image models there.
But it wasn't perfect, right? You mentioned limitations.
Definitely not perfect. It aced simple visual analogies like if A is to B, change color, then C is to what? It could do color changes, resizing.
Okay.
But when the transformation got more abstract, like complex rotations or reflections, it struggled a lot.
How did it struggle?
It often got them systematically wrong. Like it would have a consistent wrong way of applying the rotation. So true abstract visual reasoning, that's still clearly the next big challenge.
Okay, so we've seen these incredible capabilities, perception, modeling, manipulation, even early reasoning, but we need some context, right? Some
Yeah.
caveats.
Absolutely.
Yeah.
Need a dose of reality, which the researchers themselves provide. Veo 3 right now is very much a jack of many trades.
Master of few.
Exactly. If your entire business depends on absolutely perfect state-of-the-art image segmentation, a dedicated segmentation model, one designed only for that, is probably still going to outperform Veo 3 today.
Just like early GPT models were maybe cool, but not better than specialized translation tools back then.
Precisely. It's the same pattern, which leads directly to the next big constraint, prompt sensitivity.
Yeah. Getting the prompt right.
Hugely important. All those impressive numbers we said, 78% on mazes, whatever. You should think of those as a lower bound on what the model can really do.
Because getting the best result depends heavily on how you ask.
Totally. On really precise visual and textual prompt engineering. It's an art right now.
Any examples of how much difference the prompt makes?
Yeah, they highlighted the visual symmetry task. Just tweaking the prompt phrasing, it could change the success rate by up to 64 percentage points.
64 points just from changing the words.
Yep. Between the best prompt and the worst prompt for the same task. You often have to be super explicit, even use negative constraints.
Like telling it what not to do?
Exactly. Things like static camera, no zoom, no pan, no dolly. Because the model's natural tendency is to generate dynamic, interesting video, which can sometimes mess up the specific task you wanted it to do.
So prompt engineering is key right now, but does the performance scaling offer hope?
It really does. That point about pass at 10 being much better than pass at 1.
Getting it right in 10 tries versus the first try.
Right. That strongly suggests the actual capability, the knowledge, is in the model. It's latent.
We just need better ways to get it out reliably.
It's exactly. Better inference time techniques, better ways to search the possible outputs. The potential seems higher than the current first shot performance.
Okay, and what about the elephant in the room? Cost. Generating video sounds expensive.
It is, currently. Compared to, say, running a simple image classifier, generating high-res video is computationally intensive, no doubt.
So is this practical?
Well, look at the trajectory of LLMs. That's the roadmap.
Costs came down dramatically.
Dramatically. Like, inference costs dropped by factors somewhere between 9x and maybe even 900x per year, depending on the model and time frame.
Wow, 9 to 900 times cheaper each year.
So if even the low end of that trend applies to these video models.
Then generalist vision foundation models become economically viable pretty quickly.
Exactly, making this unification of the field not just technically possible, but actually practical. #outro.
Okay, so the takeaway here feels pretty clear. This transformation in machine vision, it's not just some future prediction. It seems like it's happening right now.
Yeah, the evidence is mounting. These video models, especially with this chain of frames reasoning, they're showing they have the foundational building blocks.
Perception, modeling, manipulation, and those first steps towards reasoning. Enough to start unifying the field.
And change how we interact with visual data, visual systems, fundamentally.
Like, let's talk about where it doesn't work yet. The failures are maybe just as instructive.
They really are, because for all its power, Veo 3 fails at generating a video of, say, tying a simple knot correctly. The physics get weird.
Okay, what else?
It fails to generate a plausible plan for moving big, awkward furniture, like getting a large sofa through a narrow doorway. The spatial planning isn't quite there for complex interactions. And it even fails to simulate the correct sequence of actions for, like, a robot arm to fold laundry according to real-world physics.
Right. Those are complex, real-world physical tasks, not just visual pattern.
Exactly. And that raises this really critical question, doesn't it?
Which
is this system just an incredibly sophisticated visual simulator, a fantastic special effects engine?
Or is the knowledge it's gaining by simulating the solution, by generating that movie?
Is that knowledge actually translating into genuine physical understanding? Competence.
Because if the progress keeps up, that VO2 to VO3 leap,
Yeah.
how soon before these models go from just simulating the physics of knot tying or moving a sofa
to actually planning those complex physical actions in the real world?
That feels like the crucial next step, where simulation meets reality.
That deep dive into simulating the visual world might be rapidly turning into real competence. The ability to generate the video of the solution
is maybe the first step towards being able to execute the solution.
Exactly.
And that's the thought we'll leave you with.
Thanks for taking this deep dive with us today.